Welcome to Pomodoro Joe for Friday, March 31st, 2023. Today we're doing LeetCode problem 1444, number of ways of cutting a pizza. This is a hard problem. So in this problem, we're given a pizza. It's a rectangular pizza, and it's represented by a two-dimensional array, rows and columns. Now, in this array, we have either capital letter A or a dot. Now the dot represents an empty piece of pizza, or an empty square of pizza, where A represents that piece of pizza, or that square of pizza, has an apple on it. Now I don't know why they're putting apples on their pizza. That's super weird. But regardless, this is an apple pizza. So we've got A's representing apples on that square, dots representing an empty piece of pizza or regular slice, as you can see in this diagram. Now our goal is to slice this pizza such that we have K pieces. So we are given the list, which is our pizza, and the number K. We're to slice our pizza into K pieces, and we need to make sure that every piece has at least one slice of apple on it. All right, there's one other caveat here. The way we slice the pizza is determined. We can only slice the pizza in a very particular way. We can either slice the pizza horizontally or vertically. Now, when we slice it vertically, so that's up and down, it splits the pizza into a left and a right half. So then we give the left half of the pizza to a person, and we can continue cutting the right half of the pizza using this same algorithm. If we cut the pizza horizontally, it's hard to see here, but it's at this top row. If we cut it horizontally, that's going to split the pizza into a top half and a bottom half. Now we give the top half of the pizza to one person, and then we take the bottom half as the rest of the pizza, and we can continue cutting it up using this same algorithm. So at the very end, we need to return the number of ways of cutting the pizza such that each piece contains at least one apple. All right, I'll say that again. We're returning the number of ways we can cut the pizza such that each piece contains at least one apple. And then they do say, since the answer may be huge, we need to return that number modulo 10 to the 9th plus 7. All right, there's some examples here. Here's our first example. So this is our pizza. We've got apples sort of in this funny lying down L shape. So first we can cut it at the very top row. That gives us one slice up here, and the remaining of the pizza is this part down here. Then we can slice that down this, first column, and that's going to split it into two more pieces. So we have a total of three pieces: this top slice, this leftmost slice, and this remaining rightmost slice. So that's three pieces of pizza, and our K is 3. So that's one way of doing it. Another way we can do this is it looks again here like they're slicing off this topmost row, and then they're going to slice it way over here at the very last column. So that still has three pieces, top and then left and right. These pieces are slightly different than the first way we cut it, so that's two ways of slicing it. And finally, we can just slice it down all three vertical slices, and that gives us 3 slices and 3 ways of slicing this pizza. So our answer here should be 3. Yep. Okay, let's see, we have some constraints. We have up to 50 rows and columns, and at least one slice for every pizza. Okay. All right, so this actually seems pretty straightforward. It's a recursive algorithm. We'll do a slice and take the remaining pizza and run the algorithm again. So we'll recurse. So slice, recurse until our K reaches 1. That's pretty much it. All right, well, let's put 25 minutes on the Pomodoro timer and get started. So this is going to be a recursive algorithm. We can clearly see that we take one slice, or make one slice, give that slice to a person, and then recurse on the remainder of the pizza. I could use this ways as our recursive function, but that means basically creating new pizzas for every time I recurse. So I'll have to make a copy of this pizza, take off the rows or columns that I don't want, and do the recurse. That's going to be a little bit intensive, both in runtime complexity and in terms of memory. Because every time we make a copy of this pizza, it's going to take up more memory. So if there's a way that we could do the same thing without actually making a copy of this pizza, I think I'd prefer to do that. So one way we can do that is by just keeping track of the bounds of our pizza. We won't actually make copies of our pizza. We'll just keep track of where do we have pizza left. Now I'm going to do that with an XY coordinate. So let's basically call this upper left corner our 0, 0. And Y will increase as we go down, and X will increase as we go right. So up here is 0, 0. Down here it would be 3, 3, or 2, 2. All right. So let's start with that, just defining our X, Y system. So we'll have a min and max. So let's see, our mins will be 0. So we'll just have our max X, and that's going to be the length of our list, our pizza, index 0. So we're going to grab the first row out of our pizza and see how long it is. And that's going to determine how many columns we have. So that's basically, let's grab this first row up here and see how long it is. Okay, it's 3 squares long, so that's going to give us our max X. And we actually need to subtract 1 because I want this to be the index of the max. So max X and then max Y. That's going to be the length of our pizza. That's how many rows do we have. So that's going to be 1, 2, 3. And again, we'll say -1. Now let's write an internal recursive algorithm that instead of passing a new pizza in, we'll just pass our new X, Y into this recursive algorithm. Let's define our ways recurse. And we'll take an X and a Y. And we'll take our remaining K. Let's see, I think that should be okay. I might want to rename this to something else so it doesn't conflict with our input K, but I think I'll leave it as K for now. Okay, now we have our basic recurse function header. How does this function work? So what's the first thing you always do when you have a recursive function? You write the base case. So what's our base case? How do we know that we're done? Well, that's when we have K is equal to 1. There's just one slice left and we have our remaining pizza. So we'll just say if K is equal to 1, we will return. Now what do we return? We could return 1, saying there's only one way to slice this pizza. That's no slices. We just return this remainder pizza. But what if there are no apples on this last piece? So we actually need to say, let's return 1 if, let's say it has apples. And we'll pass in our X and Y. Else we'll return 0. If there are no apples on this last piece of pizza, there's no way to do this. So we don't actually have this has apples function. We're going to have to write this. But that's our intent. We intend to have a has apple function. All right, so then what's next? I think that's our only base case. When we're down to the last piece of pizza and we have apples, we'll return 1. If we don't have apples on it, we return 0. Now we go through the two options. We can slice vertically or horizontally. So we'll say we'll slice horizontally. So how do we slice this thing horizontally? Well, horizontally, we'll be slicing across rows. All right, so that means we can slice off this first row and then recurse on the remainder part, or we can slice off the first 2 rows and recurse on the remainder of that. So we want to go through every possible horizontal slice. We want to slice the first row, the first 2 rows, the first 3 rows, all the way till we reach the end of our potential horizontal slices. All right, so that's a lot of slices, but we'll do it. So we'll call it J in range, and we'll just go from our current Y to the max Y. We'll be slicing. Now, we have to check, did the slice that we just sliced, so this piece here, we're slicing off this first row. Does that first row contain apples? Because if it doesn't, then this is not an option. We have to have at least one piece of apple on every slice of pizza. So let's see, if has apples, and what do we check? Well, we're gonna check, So now it's interesting. We don't just have the remainder of the pizza that we need to check. So this is checking the remainder of the pizza from xy to max x, max y. Now we need to check from our xy to this new xy. How do I describe that? We want to check from the current top left corner of this remaining pizza to some new intermediary corner, somewhere between the top corner and the bottom corner. All right, so our has apples can't just take an x and y, because that's going to check the rest of the pizza. We want to check the top slice of the pizza, which is going to go from our current xy, but it's going to go down to this new coordinate where we're slicing. So what's this new coordinate? Well, we have the same x coordinate because we're not slicing it vertically, we're slicing it horizontally. But the new y coordinate will be, let's see, j. I think that's right. Okay, so now we have to change our has apples. It's going to have to take not just the x and y that we're at that define the top left corner, it also needs to take the x and y that define the bottom right corner. So in that case, that's going to be max x and max y. Okay, so let's actually create our function out here. Has apples. It's going to take a, I guess I'll call it top left x and top left y, and it has a bottom right x and a bottom right y. For now, I'm just going to pass. We'll come back to this in a little bit. All right, so now we have this function. We're going through checking every possible slice, horizontal slice. If it has apples, well, then we can recurse. So our top slice has apples. Let's recurse on the remainder of the pizza. Oh, okay. I actually need to keep something else out here. It looks like I'm going to need to keep our current total, or our result. So our current result will equal 0. Now our new result, we're going to increase it by however many slices we can make from the remainder of this pizza. So that's going to be our ways recurse. And this time we'll pass in, let's see, our new x and our new y, which is going to be j plus 1, because we've sliced off the row at j. So we need to go to j plus 1. And we'll decrement our k, because we need one fewer slices of pizza. So we'll do ways recurse x, j plus 1, and k minus 1. So that's our slice horizontally. What about slice vertically? Well, it's pretty much the same thing, except we'll be doing it on the x-axis instead of the y-axis. So for I in range from x to max x, we'll say if it has apples. So now we're going to be checking this leftmost column for apples. Well, that's going to be from our I. No, it's still our x and y, but now it's going to go to our current I and y. Now, if that still has apples, well, then we can increase our result by the number of ways we can recurse on the rest. This time it's going to be I plus 1, y, and k minus 1. Now, once we get through all of that, we can return our result. Okay, now there's still a couple pieces we have left. So we have our base case up here. If we've gotten down to one slice, we'll just return whether or not that slice has an apple on it. We can slice all horizontally, we can slice all vertically, and we can recurse on each of the remainders. Now the last thing we need to do, well, two things left. We actually need to define our has apples, and then we also need to make our initial call. So let's make our initial call so I don't forget that. So we're going to call ways recurse, and we'll just start at 0, 0 with our initial k. Okay, how do we figure out has apples? Well, let's start it with false. So we'll say, let's assume it doesn't have apples. And at the end, we'll return that result. So now we need to go through every cell in these rows and columns between the top left X and Y and the bottom right X and Y and see if there are any apples. So for I in range, let's see, we'll start at the top left. I'm going to do Y first here. So for J in range, we'll go in the top left Y to the bottom right Y. And we want to be inclusive, so I think we need to add 1. And then for I in range, from the top left X to the bottom right X plus 1. If this square has an apple, we can return true. Otherwise, we keep going. So if pizza, and we do Y first and then X, because Y's are the rows and X's are the columns. So we'll do J and I. Maybe I should call this, well, no, it's fine. That's fine. So if that is equal to a capital letter A, we have an apple, and we can just return true. All right, this is looking pretty good. I think this might work. Let's just take a quick look here. So we've defined our bounds. We have a max X and Y. We have our function has apples that takes some subset of our X and Y by defining the top left corner and the bottom right corner. We'll go through every single row and column, checking every cell. If it's an A, we've got an apple and we can return true. Otherwise, when we get to the end, we return false. We can maybe modify this a little bit. Let's not have a result. We don't need this. Clean this up just a little bit. All right. And then we have our recursive function. So it's going to take our top left corner and the number of slices we need. If we have 1 slice left, we'll just check to see if that slice has apples on it, and we can return 1 if it does. That's one way we can slice this. If it doesn't, we have to return 0. All right. Then we'll go through, we'll have every possible set of slices. So we'll slice at 1, and then at 2, and 3, and so on and so forth, calling recurse on that remainder of the pizza as long as the slice that we sliced off has apples. Okay, I think this is going to work. And then we slice vertically and we return the result. Now the last thing that I totally forgot, we actually need to return the answer modulo. Let's see, it's going to be the power of 10 to the 9th plus 7. Okay, let's see if this works. All right, we're missing something here. Output 2, expected 3. So what are we doing wrong? Oh, this is what I'm missing. This should be max X, and this should be max Y. Otherwise, we're only checking 1 square. Okay, that was my fault, yes. So we need to go from our XY coordinate to the max X for this current J. So this should work. Okay, that works. Let's give it a shot. It's taking a long time. Time limit exceeded. Okay, well, we made 52 out of 53 test cases, so we are close. We just need to improve our speed a little bit. And luckily, Python is really good at this. I have a trick up my sleeve. We are going to use caching. So from functools, import cache. Now, cache is a function decorator that, given the same inputs, it will return the same output. It'll cache the output. So the first time you run this function with a unique set of inputs, it will run the function, it will cache the output. If you call this function again with the same inputs, instead of running all of this calculation, it will just return the cached value for these inputs. So we just decorate the function with cache. So at cache, and we can do the same for this one, in fact. So we'll decorate both of our functions with the caching decorator. And now this should give us some boost in our speed. And we pass. Oh, look at that. We've done every single problem in March. Fantastic. So we beat 31% for runtime and 5% for memory. All right, not great, but not too bad. Let's see if we can speed this up. We've got about 5 minutes left. All right, I've got a couple tricks up my sleeve here. So one thing we can do, let's see, right now we're just going through returning true. This one, I don't know if there's a whole lot I can do to speed this up. As soon as we find a value, we return. So it's not like we're waiting around to find the false value. So not a lot I can do to speed this guy up. Now this guy, again, not a lot I can do to speed this up. But I'll tell you what I can do to speed this up. So in here, we're saying we're going to slice at this horizontal slice, and then we're going to check to see if this has apples. Now, if this top slice had an apple, and we go down to the next slice, well, we know that it's going to have an apple because it includes that top slice. So we don't need to actually run this whole thing again. Same thing on the vertical slices. If we make a vertical slice and we take a look at the piece that we're giving away and it has apples on it, then we move over and make the next vertical slice. Well, we know that includes the piece that has apple on it too. So we don't need to do this whole calculation again. Let's just cache that out here. So let's say has apples, and we'll set it equal to false to begin with. Now, if this has apples, or we check to see if it has apples. Maybe I should call this has apple cache or something. But if we already know it has apples, or if we check and we find out it does have apples, then we can set the has apples to true here and do our recurse. Same thing on the vertical. We can say has apples. Now if we get in here, all right, so that should actually cut out a whole bunch of processing. All right, let's try this. Will this still work? Looks like I missed something. Oh, because I called this function has apples. So I can't call this has apples. I'll call it has apples cache. All right, if has apples cache. Then we need to set that equal to true. All right, that should work. Okay, let's see how much it saves us. And that is a huge win. Now we're at 98% for runtime and 9% for memory. Huge gains. So just by making that small change, caching out the values, we went from a 31% runtime to a 98% runtime. All right, we're down to 2 minutes, so I'm gonna leave it there. Check this one out. Try it on your own. See if you can improve on this. Maybe you can get a better memory footprint. I bet you can. All right. All right, that's it for me. Hope you enjoyed this. Hope you had fun. Hope you learned something. Please like, please subscribe. It really does help. And please go out and write better code.